All right, we'll go ahead and get started. Just a quick question at the beginning. Chapter 17 study guide that I put on Learning Suite on the front page actually says Chapter 23. That's a holdover from a previous edition of the text. I'm sorry, it is Chapter 17 in this text. All right, another question that has come up about the exam was that the Learning Suite or the syllabus says something about the exam ending at 9 p.m. tomorrow, but it has been pointed out that the testing center actually closes at 10. No, I do not expect you to turn in your exam by 9 tomorrow, just whenever the testing center closes. Let's see. Anything else? Any other questions you want to ask about the exam? On the practice test, Chapter 16 has problems listed from Chapter 22. Should we assume that those are just from 16? I meant to correct that, and I corrected most of them. Just ignore the problems that say they're from 22. I think most of them are in the Chapter 16 practice test. I think most of them are correct, but just ignore the ones from 22. Because the problem numbers change from text edition to one edition to another. All right. Well, I'm sorry to have to do this by Zoom again. I should be good to go for class in person on Friday. I'm not feeling bad at all. I'm just taking enough precautions so that I don't infect anybody. At this point, I've been vaccinated, boosted, and had COVID, so I'm about as immune as you can get, I can imagine. Anyway, I realize that you're in the middle of a test, and so you're not excited to get on to new material today, and that's fine. I understand that most of you won't have read this section as we get going, and that's fine. Just take a step back, listen, try to learn, and then as you have time in the coming days, you can come back and review. But I would recommend reading the stuff in the study guide carefully, because that's going to help you a lot. So to begin with, we've been talking about carbonyl compounds, and our focus so far has been on the carbonyl carbon. Our focus in chapters 17 and 18 shifts to the alpha carbon. And this is really important because a lot of key reactions in biology involve the alpha carbon. So we're going to spend our time today talking about the acidity of the alpha carbon. And as we get to the end of today's lecture and next time, we're going to talk about using what are called enolates as nucleophiles. So you may recall from a long time ago in 351 that the pKa of a run-of-the-mill carbon-hydrogen bond, sp3 hybridized carbon-hydrogen bond, is around 50. In contrast, the pKa of a proton that is alpha to a carbonyl, in this ketone, the proton that's alpha to the carbonyl is 20. So that's a 30 order of magnitude difference in acidity. This proton is 10 to the 30 times more acidic than that one. So, and we can consider the reason for this by drawing the conjugate base. Now I'll point out, just as in case this is unfamiliar to you, we're using the Greek letter alpha to represent a position that is one bond away from a functional group of interest. If it were 2 bonds away, it would be beta, and so on. So this is the alpha carbon, and this is the alpha proton. Now, if we draw the conjugate base of the enolate, we can see that it has 2 possible resonance structures. Either one is acceptable. And what you conclude from these resonance structures is that the negative charge on the alpha carbon in the conjugate base is actually shared with the carbonyl oxygen as well. Remember that resonance structures are both incomplete descriptions of the actual structure of the molecule, and so the enolate is electron rich on the alpha carbon and on the oxygen. But it's this resonance delocalization that makes the enolate more stable than the conjugate base of our regular sp3 hybridized carbon, where that's a completely localized charge. So resonance delocalization is key for why that alpha proton is more acidic, because the conjugate base is stabilized by resonance. I just briefly wanted to mention the MO picture of enolates. You may have gotten some of this in the chapter on conjugation and dienes and the Diels-Alder reaction. If you didn't, it's not that big of a deal, so just try to get the main gist of things. It turns out that whenever you have a conjugated system, there's an interesting strategy you can use in terms of MO theory to explain what's going on. Look at these two resonance structures, and you can see that by virtue of the fact that there's a pi bond here and a pi bond there, you can conclude that on the carbonyl carbon, on the oxygen, and on the alpha carbon are 3 p orbitals that line up. I'm going to draw them briefly just to indicate we're looking down from above, and that's sort of side by side they would overlap. Okay? Now you can actually mix 3 orbitals together to get three new pi molecular orbitals. And I'll show you what those 3 pi molecular orbitals are. I won't ever require you to generate these from scratch. And if you want to know more, there's some more information in the optional MO theory study guide on Learning Suite. Notice that there are 2 places where there's negative charge. And if you look at the electrons that are involved in resonance, you have the lone pair, and then you have the pi bond. And in the resonance structure, the pi bond is there, and the lone pairs are there, something like that. So there are 4 electrons involved in resonance, and that means there are 4 electrons involved in this system of pi orbitals. If we look at these orbitals in the same way that we saw them up here, sort of looking down from the top, and we put oxygen here, carbonyl carbon there, and alpha carbon there, the lowest energy orbital looks sort of like this, schematically anyway. It's what you get when you mix 3 p orbitals together side by side in phase. Actually, if you want to know what it really looks like, it would be kind of like a big, long super pi bond that extends over all 3 atoms. Okay, and the electrons in this orbital correspond to the electrons that are spending their time in between carbons 1 and 2 in a pi bond, and in between carbons, the carbonyl carbon and the oxygen in the pi bond. The next orbital schematically looks like this. And again, this is I don't want to spend too much time on this or belabor the point, but it does have some interesting conclusions. And we're using color here for sign of the wave function. Whenever we go from one color to another, that means we're going through 0. Places where the wave function equals 0 are called nodes. This node happens to coincide with the carbonyl carbon. And so these higher energy electrons, the high energy pi electrons, are only ever on the oxygen and on the alpha carbon, which is exactly what resonance tells you, that the negative charge is on the alpha carbon and on the oxygen, but never on the carbonyl carbon. One other interesting feature is actually that comes out of the MO theory calculations. It's not something I would expect you to predict, but it's useful in explaining some of enolate reactivity. The orbital actually here, the highest occupied molecular orbital, is actually mostly on carbon and only a little bit less on oxygen. So it turns out that the highest energy pi electrons is mostly on the alpha carbon. So we're going to see that when enolates react, they are mostly reactive on the alpha carbon. Okay, so that's a quick crash course in enolate MO theory structure. Because of the fact that enolates are going to be reactive on the alpha carbon, my enolate resonance structure of choice is going to be this one on the left, in which we have the negative charge on the alpha carbon. Though you can also use this one and it's fine. Why is it mostly on the alpha carbon? It has to do with the electronegativity of oxygen. And there's some, the full explanation of that would require a little bit more background in MO theory. And if you want to know more about it, we can talk. Basically, think about this lowest energy orbital is polarized towards oxygen. Oxygen's more electronegative, so it pulls the lower energy electrons more towards itself, and correspondingly, the higher energy electrons end up more on the alpha carbon. That's not a great explanation. It comes from the math of MO theory, basically. Okay, other questions you want to ask about that? All right, so let's now talk about different kinds of enolates, because we've had a huge number of carbonyl compounds that are not just ketones. So we need to consider what carbonyl structure does to how carbonyl structure and alpha carbon acidity are related to each other. Before we do that, though, I want you to look at this resonance structure. Remind yourself that the reason why the enolate is acidic is, or why the alpha carbon is acidic. Oh my gosh. Sorry, I'm trying to draw at the same time as I'm talking and it's not going very well. The reason that the alpha proton is acidic is because you've got a resonance structure where you can delocalize that negative charge. And in part, this resonance structure works because the carbonyl carbon is electron poor, and there's an electronegative group over here that can accept the electrons. It's almost as though the alpha carbon is donating electrons into the carbonyl carbon, and then you have the negative charge on the oxygen. So if the reason that the alpha proton is acidic is because the carbonyl carbon is electron poor, then more electron poor carbonyls should have more acidic alpha protons. But the cool thing is that we already know a lot about how electron-poor carbonyl compounds are, because we have just finished a chapter where we talked about amides being less reactive than esters, and the argument had to do with how electron-poor the carbonyl carbon is. Okay, so here is an ester. Here's the conjugate base. And did I say ester? That's an amide. I'm sorry. Here's an amide. Here's the conjugate base. Gosh. Amides have an additional resonance structure in which lone pair electrons on the nitrogen can donate into the carbonyl carbon. And as you can imagine, in the conjugate base, that kind of thing should be destabilizing, right? Because the alpha carbon is already donating electron density into the carbonyl carbon and putting a negative charge out on the oxygen. And then the nitrogen can do the same. And that means that the conjugate base of the amide is destabilized. Another way of looking at this is simply to draw that resonance structure of the amide starting material and realize that once you already have a negative charge on the oxygen, removing this alpha proton is not going to be very favorable, because then you're going to have two negative charges close to each other. Would molecules with a halogen or other electron withdrawing group act the same and have similar properties? If you had an electron withdrawing group, you would expect the alpha proton to be more acidic, though you're going to have a competing competing elements of reactivity, right? How acidic is the alpha proton versus how nucleophilic is the carbonyl carbon? All right, the pKa of the amide is 30. Now, here is the ester, right? And we can draw a similar resonance structure for the ester of the for the conjugate base of the ester as we did above for the amide. That is, here is the enolate, here is the resonance structure where the negative charge is on the oxygen rather than on the alpha carbon. And then here is the resonance structure you get when it's that ester oxygen that does the donating into the carbonyl carbon rather than the alpha carbon. And as analogously with the amide, the electron donating ability of this oxygen makes the alpha proton not as acidic as you would expect based on what we learned above for simple ketones, where the pKa is 20. In the case of the ester, the pKa of that alpha proton is 25. Now, why is that the case? Remember that the more electron-rich the carbonyl is, the less acidic the alpha proton will be. Nitrogen is a better electron donor than oxygen because oxygen is more electronegative than nitrogen, right? So what we're saying is the ester is not as electron rich as the amide, and therefore the ester has a more acidic alpha proton than the amide does. Notice that the electron richness of the carbonyl also tracks with reactivity in nucleophilic addition and substitution or substitution reactions. All right. So now let's compare both of those with the ketone. Why is the alpha proton on the ketone not as acidic as on the ester? And the answer is that we can draw the conjugate base of the ketone. Oh, shoot. Okay, we can draw the conjugate base of the ketone. The methyl group is not as good a donor, an electron donor, as are our oxygen or nitrogen. Oxygen or nitrogen are both resonance donors. The methyl group, the alkyl group, could be methyl, could be other alkyl groups, is electron donating because sp3 hybridized carbons are less let me back up. The alkyl group is electron donating because sp3 carbons are not as electronegative as sp2 carbons. And so the sp3 carbon will donate electron density into the carbonyl, and that is what is called an inductive effect. For the alkyl group, it's an inductive effect. For the amide and the ester, the resonance effect dominates. The inductive effect isn't as strong as the resonance effect, so the ketone is less electron rich than the ester, and so the pKa is 20. And in agreement with this, actually, if you measure the pKa for the aldehyde, which has only one alkyl group, and here is the conjugate base, that's even less electron rich, and that has a pKa of, I'm going to get this wrong, so I better look it up, 17. Okay, and again, this tracks with carbonyl reactivity, aldehydes and ketones being more reactive than esters or amides. Okay, that was maybe a little bit convoluted, so I want to pause for questions. What questions do you have? Okay, if you think of anything, go ahead and put it in the chat. Oh, here we go. All right. So it turns out that if the thing that makes an enolate or makes an alpha proton acidic in the first place is the presence of this carbonyl and the availability of this resonance structure that delocalizes the negative charge, you might imagine one way to make really acidic alpha proton would be to make the proton alpha to two carbonyl groups. So here's an example of a molecule where the alpha proton is adjacent to two different carbonyl carbons. By the way, just for review, ET means an ethyl group, ME means a methyl group, and so on. We'll sometimes use those abbreviations. Another thing that will come up as we talk about these compounds is if you start counting at one of the carbonyls, this is the alpha carbon, and then you could say the other carbonyl carbon is the beta carbon. And it turns out it doesn't matter which carbonyl you start counting at. Which carbonyl you start counting at, the other carbonyl is on the beta carbon. This is called a beta diester. Or sometimes more broadly we'll call these beta dicarbonyl compounds. I'm not going to test you on that nomenclature. However, I will talk about beta carbons and beta dicarbonyl compounds a lot. recognizing them as an important structural pattern because there's some unique chemistry that can happen with these molecules that we'll get to later. So just be aware of that nomenclature. Now I'm seeing a question from some previous stuff, so let's pause. And I think the TAs are trying to address this. More resonant structures, if there are more resonant structures, doesn't that make the conjugate base more stable? Yes, if the resonant structures are good and don't involve repulsive interactions. And that's the real problem with this resonance structure for the amide, where you'd have a negatively charged oxygen right next to the alpha carbon. So yes, in general, resonance is stabilizing, but there are some resonance structures that are better than others. This one is actually destabilizing. Okay, so the pKa for this compound is 13. And the reason that alpha proton is so much more acidic is if you draw the enolate, you can see pretty quickly how we can actually generate other high quality resonance structures in which there'll be two options in addition to the one where the negative charge is on the alpha carbon. You can have that negative charge go on the first oxygen of the ester, or you can have that negative charge be delocalized this way. So there are more places to delocalize the negative charge onto oxygen, and that negative charge is now spread out over more atoms, and the resulting conjugate base is even more stable. Notice this pKa is less than the pKa of water. So this alpha proton can be totally removed using OH minus or some alkoxide. And that's important for reasons that we'll get to later. If you continue to follow this trend, the idea that if your carbonyl is more electron poor, the alpha proton is going to be more acidic. This then allows you to make some predictions. For example, if we take the same ester but replace the beta ester with a beta ketone, incidentally, that's a beta keto ester, that alpha proton has a pKa of 11. Why is it more acidic than the beta diester? Because ketones are more electron poor than esters. And similarly, you can push this to various lengths, and your text has even more examples of beta dicarbonyl compounds. The beta diketone has a pKa of around 9. So the basic principles are the more electron poor your carbonyl is, the more acidic the alpha carbon is, the alpha proton is. And then if you have two different, if your alpha proton is alpha to two different carbonyls, that's more acidic than if it were alpha to only one. Okay. So recognizing that alpha protons are acidic and recognizing trends in acidity is important. We're going to keep coming back to these pKa's because they're going to influence the course of a reaction. So Tyler's asking back on the aldehyde, why the aldehyde is more acidic than the ketone. Remember that the difference has to do with, this alkyl group versus this hydrogen. Methyl group is an inductive electron donor because sp3 carbons are less electronegative than sp2 hybridized carbons. So the sp2 carbonyl carbon can actually pull electron density away from the methyl group. And so the more methyl groups you have adjacent to the carbonyl, the more of this inductive effect you get. But in contrast, the proton is not a donor. So the aldehyde is more electron poor than the ketone, and therefore the aldehyde alpha proton is more acidic than the ketone alpha proton. All right, other questions? All right, let me give you some context as to why pKa's are important for enolates. We're going to consider two different contexts for making enolates. The first we're going to call equilibrating enolate formation. Equilibrating or reversible enolate formation. This is going to be when we use a base that's not strong enough to totally remove a proton from the carbonyl compound. So imagine bringing this ketone that we've dealt a lot with already, and we know the pKa is around 20. And imagine we try to use a base like ethoxide, and we ask what the position of this equilibrium is, where the ethoxide removes the alpha proton from the enolate to give you ethanol, and then, ethoxide removes a proton from the alpha proton. Sorry guys, the ethoxide removes the alpha proton from the ketone to give you ethanol and the enolate. Sorry for getting tongue-tied. And actually the pKa of that hydrogen on ethanol is around 16. So if you turn this into a chapter 2 problem from 351 and ask which side of the equilibrium dominates, you would conclude that this equilibrium favors starting materials way more than products by about 4 orders of magnitude, meaning at equilibrium you would have greater than 99.99% of the starting ketone and the alkoxide, and less than 0.01% of the enolate. Okay, this is reversible enolate formation. Why would you ever do this? First, even though this is only a very small amount, remember that there are a huge number of molecules in a mole, like 10 to the 23rd. And 0.01% of 10 to the 23rd is still a really large number. And therefore, there is still enough enolate to do chemistry. And we'll talk about what we're going to use enolates for in a little bit. The other reason you might want to do this is because the alkoxide bases are, or even hydroxide, are cheap. They are not air sensitive or moisture sensitive, so you don't have to take special precautions when using them. They're just easy to use, and so if you can get away with it, why not? And for simple ketones like this, it's really not a huge deal. However, if we make our ketone just a little bit more complicated, then we've got a different situation. So let's use this ketone where we have 2 different kinds of alpha carbons, 2 different kinds of alpha protons. One on the less substituted side, one on the more substituted side. So let's consider, we know that, and let's use, again, ethoxide as our base. So we know that no matter which proton gets removed, equilibrium is going to favor the starting material, right? Let's draw the enolates, though, that would come from this starting material. If we remove the purple alpha proton, we end up with this enolate, which we could draw a resonance structure for, and it would look like this. If we remove the orange alpha proton, we get this enolate, and we could draw a resonance structure that looks like this. All right. Now, still, we're going to have 99.99% of our starting materials, but let's talk about which enolate should be present in a higher amount. Okay? And to do that, we compare their stability. The reason we can compare their stability is if purple enolate is in equilibrium with starting enolate, and if orange enolate is in equilibrium with starting ketone, let me back that up again. If purple enolate is in equilibrium with starting ketone, and if orange enolate is also in equilibrium with starting ketone, then orange and purple enolates are in equilibrium with each other. And if they are in equilibrium with each other, then the most stable enolate should form in the larger amount. Okay, so let's talk about enolate stability. Enolate stability tracks with alkene stability. And you remember from 351 learning that the more substituted alkenes are more stable. Same with the enolate. The more substituted enolate is more stable. Whereas the orange enolate, which is less substituted, is less stable. All right. So of the two enolates at equilibrium, which is present in a larger amount? The purple one is going to be our major enolate, and the orange one is going to be our minor enolate. Now remember, we do not mean to communicate that this enolate is the major product of these reaction conditions, because it is not. That enolate is still present in a very, very small amount, right? All we are saying is, relative to the purple enolate, the orange enolate is present in even smaller an amount. And this is important because I said even a small amount of enolate like this is enough to do chemistry. And so if we have a reaction for this enolate to do, or if we have, what I mean to say is if we now expose these enolates to an electrophile, the major product we get is going to be from the more substituted enolate. Let me give you an example of the type of reactions that you might want to do. So suppose you took this starting ketone and you generated with sodium ethoxide, you generated a very, very small amount of enolate, and then in a second step you add an alkyl halide. Now, even though there's only a very small amount of either enolate, if you can react that enolate as a nucleophile, thank you, Craig. I am very, very, very sorry. If you use the enolate as a nucleophile and react it with this alkyl halide electrophile, that's going to draw off the enolate via Le Chatelier's principle, and that will cause more of my starting material to go this direction. So let's draw the product that would happen if you added an alkyl halide to this enolate. And The enolate is going to be reactive on the alpha carbon for reasons we talked about earlier. You can use it as a nucleophile in an SN2 type reaction. This is called enolate alkylation, and the product you would get from the more stable, more substituted enolate looks like this. In contrast, if you had the less substituted, less stable enolate react with the alkyl halide, then your product is going to be different because the new bond we made is here for the orange product versus here for the purple product. We have two regioisomeric possibilities. Regioisomers is the same as constitutional isomers. They are isomers that differ in connectivity. You got two regioisomeric possibilities, but the fact that the purple enolate is more stable means that this one is the major product. And so we can say that this reaction is regioselective for the product that comes from the more substituted, more stable enolate. So we would draw as the major product for this reaction something like that. Okay? All right, what questions do you have so far? I think that may have been convoluted, and there, I'm sure, some questions or issues that need resolving. So go ahead. Any questions? You can type them via chat too. Sorry, go ahead. Hello? All right. I didn't quite hear that question. If somebody was asking something over the audio, go ahead and type it because the connection was weird and I couldn't quite hear. And the whole reason, let's just review, the whole reason that we get the major product from the more substituted enolate is because we're doing this reaction under reversible conditions. So that if the base removes the orange proton first, that's fine. It's going to go back to starting material. If it removes the purple proton, that's fine. It's going to go back to starting material. On average, there's more of this enolate than this one. And so this one is going to dominate as the nucleophile. Does this pattern change if you have something other than a methyl group attached to the two alpha carbons? Well, let's look at that. So maybe the real question is, are the two alpha protons different? And is there a large enough difference that you can expect some regioselectivity in terms of the major enolate and the major product? So as an example, here is a carbonyl compound where the two alpha protons are identical. So you'd get no selectivity there. In contrast, if you had one side with an alkyl group on it and the other without, you would get the major product under these reversible conditions from the more substituted alpha carbon. Okay, so moving a little bit backwards, summarize again what makes an enolate more reactive. Okay, well, I think we're convoluting a couple of things. We're talking about acidity of the alpha proton was what we did first. The more acidic, the more electron poor the carbonyl is, the more acidic the alpha proton will be. So that's a separate issue. That's before you even make the enolate. How hard is it going to be? Then when you have two carbonyls that are adjacent to the alpha carbon, that becomes even more acidic. But that's all about the ability to even get the enolate in the first place. Talking about enolate reactivity was dealing with this equilibrium where we were saying there's simply more of the more stable enolate than of the less stable enolate, so that's the one that acts as the nucleophile. Why do I use the term major product in the reaction with the alkyl halide, but major enolate here? Because this enolate is not a product, it's a high energy intermediate. That's why it's present in only a small amount. It's just that there's more of this one than there is of that one. And next time I'll draw an energy diagram that will hopefully illustrate that a little bit better. But the idea is that once you add something for the enolate to react with, you disrupt the equilibrium and perturb it towards this direction, and so all of your starting material, or most of it, ends up as this major product because there was never very much of the minor enolate at all to react with the alkyl halide. Will the major enolate always give you the major product? Yes, the major product comes from the major enolate. I will say that sometimes the regioselectivity between these products is not 100%. So you can expect different product ratios depending on context. I would only, if I can imagine a situation where I would give you a question and say, which of the following is the major product of this reaction? And then you would choose this option. But in reality, this the selectivity is sometimes not as good as one might hope. Other questions? Oh, yeah. Declan, I think I've maybe just addressed that. In a test situation, should we expect to see both the major and minor product shown in the same answer, or would you want us to pick the major product? Yeah, I would. The question would tell you what to do. If I said which of the following is the major product of this reaction, you would choose, for this particular case, you choose the one that you get from the more substituted enolate. Alternatively, yeah, I guess that's probably the way I would ask that question. Not thinking of an alternative. I suppose I could ask the question, no. I don't want to speculate without thinking it through because I will make you guys worried. So, but yes, being able to recognize the major product as having come from the more stable enolate is important. All right, other questions? I guess before moving on, there are some things about this reaction that should maybe give you a little bit of heartburn. One of them is you're using ethoxide as a base, but only a very little amount of the enolate forms. So most of your starting material is sitting around as these two things. And then you're adding alkyl halide. And in 351, you guys spent all kinds of time having alkoxides react with alkyl halides via an SN2 reaction. I'm talking about getting an ether product like this, right? That's just the Williamson ether synthesis. Well, is that a competing reaction? Does that sometimes compete with the with modification of the enolate with this alkyl halide? Yes. And so the text introduces this reaction because it's a simple way of seeing what you could do with enolates. But in practice, it's not that effective. You can, in terms of synthesis or predict products, you can pretend like it works perfectly, but in practice, it's not as effective because of the possibility of a competing ether formation. I guess that's all we have time for today, so we'll finish there. Good luck on the test, and I will see you all in person on Friday. Totally off topic, but where did I get my Darth Vader and Stormtroopers on Abbey Road shirt? This is embarrassing. My mother gave it to me. I'm 42 years old, and my mom